Hi again. In this video, we are going to distinguish between two different kinds of discontinuities. They are called removable and non-removable. So those are the two categories that all discontinuities will fall into. I think I should be a little more specific here, actually. They don't fall into both. All discontinuities fall into one of these two categories, to be a little more precise about that. Okay, so the first kind, like I mentioned, is called removable. Removable discontinuities. We kind of used this word in the past when we were talking about limits and finding with 0 over 0 and kind of removing a whole. So that's exactly what we mean when we describe a removable discontinuity. So these result from a hole in the graph. And they can be, quote unquote, removed or filled in using algebra. We talked about several different ways of doing that when we were looking at limits. Some of those methods included factoring and canceling, rationalizing, maybe combining fractions together. I just want to point out again that when you remove a whole, you get a new function, but with limits, it doesn't matter, right? Because you don't actually see what happens at that point when you're finding a limit. But anyway, discontinuity, when you have a whole, we'll call that removable. So algebraically, this would give you 0 over 0 when you plug in the value. So 0 up top and 0 on the bottom. These will have the same factor in the top and in the bottom. That gives you the 0 up top and 0 down bottom. Okay, the second kind is called non-removable. Non-removable discontinuities. So these cannot be removed using algebra. These result from, graphically, a vertical asymptote. Or a jump in the graph. And again, these ones cannot be removed or filled in by using algebra. So algebraically, if you were looking for these, then a vertical asymptote would be given to you or shown by having a 0 in the bottom and some other non-zero number up top. So I know 0 is a number, but a vertical asymptote comes from a non-zero number in the numerator and a 0 in the denominator. A jump happens when, again, you have like a piecewise function or something like that. So these aren't too hard to determine graphically. We do want to shy away from saying things like whole or vertical asymptote when describing a discontinuity. We want to use these fancy math words of removable and non-removable. So let's take a look at some examples of finding and classifying all discontinuities. So I just have two examples here. The first one is g of x equals x minus 2 over x squared minus 4. Now, when we're finding discontinuities with a rational function, those are going to occur when the denominator is equal to 0. But we need to determine, basically, if the top is 0 or not at that same x value. So when we're finding discontinuities and classifying those, we want to factor both the top and the bottom, or the numerator and the denominator, completely. Okay, so in this case, what we have is x minus 2 up top. That's totally factored. In the bottom, we have a difference of 2 squares. That'll give us x minus 2 times x plus 2. Okay, so we have discontinuities, right? If you just look at the denominator, they're going to happen when x equals positive 2 and when x equals negative 2. Okay, so let's just write down that we have those, and then we'll see how to classify those. Okay, so remember that removable means essentially that you can, I don't know, like cancel out that factor. So where is the x equals 2 coming from, right? That, of course, is coming from here. And then here we have the discontinuity of x equals negative 2 as a discontinuity. The one that gives us the x equals positive 2 has the same factor in the numerator. So when you plug a positive 2 in, you're going to get a 0 up top and a 0 in the bottom. And so this is going to result in a hole. Okay, so anything that you can cancel out like this or remove, that's what we would call a removable discontinuity. Okay, so we can cancel these. They're the same here and here. So this one would be removable. Okay, so the x equals 2 is removable. But the other one, the x equals negative 2, came from this factor. And there's nothing, like when we plug a negative 2 into the function, the g of x, we're going to get, let's see, negative 2 minus 2. So that's negative 4 up top. We're going to get negative 4 in the top and a 0 in the bottom. And so that results in a non-removable discontinuity, or graphically a vertical asymptote. So this one is non-removable. There's no factor that you can cancel it out with. And that's the gist of how we determine the type of discontinuity algebraically. This is it. This is what we have to do to decide that. So, yep, it's a little too bright for my liking. There we go. All right, let's take a look at one more example. F of x equals x cubed. Oh, I got 2 more actually. X cubed minus 9x over x to the 4th minus x cubed minus 12x squared. Okay, so remember what we want to do is factor the numerator and the denominator completely, or factor the top and bottom all the way. Okay, so in the top, it looks like we have a GCF of an x that we could take out. We'll be left with x squared minus 9. In the bottom, it looks like that we have a GCF of x squared we could take out. Okay, that'll give us x squared minus x minus 12. And I think we can factor further. Right? We want to factor it completely all the way. In the top, we have a difference of 2 squares here. So that can factor into x plus 3 times x minus 3. And we still have that x out in the front. Okay, down here, we still have x squared. I guess we could technically factor that into like x times x. So let's just do that. Then down in the bottom, we have a quadratic that will factor into x minus 4 times x plus 3. Okay, so we want to kind of list all of the discontinuities first. So what have we got here? Looking at the denominator, we're going to see what makes a denominator 0. Well, we've got basically 4 different factors here. This first and second factor, these will both give us the discontinuity of x equals 0. Right? If we plug in a 0 for x, we're going to get a 0 in the denominator. This factor here gives us a discontinuity at x equals positive 4, because if we plug a 4 in for x, we'll get a 0 in the bottom, and all that stuff multiplied will just give us a 0 in the denominator. And then lastly, we have this x plus 3 factor, and that will give us x equals negative 3 as a discontinuity. Okay, so we just have to decide if these are removable or not. So you just want to look and see like what can we kind of just cancel out. Like, so if we start with x equals 0, so that's coming from both of these. Okay, so if we can look at the numerator here, it looks like we can cancel this x and cancel that x. But it's kind of like still there, but there's still an x in the bottom. So we weren't able to remove it all the way. Even though we removed part of it, there's still that x in the bottom. So ultimately, it's not fully removable. So we would call this one non-removable. Okay, so this one's non-removable. I know it's a little confusing, but if you can't take it all out in the bottom, then ultimately it is not fully removable. Okay, then we've got x equals positive 4. That one doesn't have anything for it to cancel out with in the numerator. So if we plug in a positive 4, we're going to get a 0 down in the denominator. We won't get a 0 up top in the numerator. So this one also will be non-removable. Then we have, I can note this over here as well. It doesn't cancel with anything. So that's just kind of stuck down there. Then we have x equals negative 3 from this factor. And of course, this one has a common factor up top. Right here, we can kind of remove those. And so this one we would say is removable because we get rid of it completely in the denominator. So x equals negative 3 is a removable discontinuity. So we found all the discontinuities and classified them, and we did our job. So yeah, the idea with rational functions is just to divide both top and bottom, see if there's common factors across the division, across the fraction bar. If so, it's removable. If not, then it's not. That's the idea with that. Okay, the last kind here is not a rational function. It is a wonderful piecewise function. So let's find and classify all discontinuities here. So this function is made up of 2 quadratics. You've got a quadratic for x less than 2, and then a different quadratic for x greater than or equal to 2. Now, in a previous video, the way that we saw if a piecewise function was continuous was by graphing. So you can definitely do that. I'm going to show you like a shortcut for finding if this piecewise function is continuous. And I'll just kind of share with you the idea of that. So, and then we can also sketch a graph too. So each of these pieces on their own will have no discontinuities. Right, they are polynomials. And remember that polynomials are really well behaved. They don't have any poles or asymptotes. The only possible place, the only possibility for a discontinuity in f of x in the whole function is where the function switches at x equals positive 2. So that's really the place that we need to focus on. Now, if there's going to be a jump, then the y values from either side aren't going to match. But if they do meet, then there won't be a jump in the graph. Okay, so what you can do is basically just plug in the 2 into each of these and just see if the y values from left and right are meeting or if they're not. Okay, maybe they're meeting together, they have the same y value, or if they're not, they would have different y values. Okay, so we're just going to take this one here, plug in x equals 2. Now I know that we don't actually plug in 2 into this function. However, what we're really doing is finding like what would the y value be or what is it limiting towards as as x approaches 2. So if we just plug in a 2 here, that's going to give us 2 squared minus 4 times 2 plus 6. So it's 4 minus 8 plus 6. 4 minus 8 is negative 4 plus 6 is positive 2. All right, then we're going to also plug in 2 into here and see if they meet up at that point where they're glued together. So we'll have negative 2 squared plus 4 times 2 minus 2. Okay, negative 2 squared, remember your order of operations. This will be 2 squared first, which is 4. Then you negate it. So it'll be negative 4 plus 8 minus 2. Okay, negative 4 plus 8 is positive 4. Minus 2 is positive 2. Oh, so these are meeting together in the right spot. So it looks like this one is going to have no discontinuities. And that's okay. If there was a discontinuity in a piecewise function, then you can't remove it because it's not really, holes are the only thing that's removable. Non-removable ones would be a jump, and piecewise functions could have a jump in them. So that's how you would classify something of a discontinuity. With a piecewise function, if it happened, you would have a non-removable one. Okay, so this is the end of this little section here. I hope the concept makes sense, at least intuitively, of continuity meaning connectedness. That's really the idea. Of course, the math and the symbols and the little pieces and stuff are what trips us up a lot. So take some time to practice. You've got some WebAssign on 1.6 and also some questions on your written homework number 2. And please stop by office hours or send me an email if you have any questions. Hope you have a great day, and I'll see you soon.